So, good afternoon, everyone. I hope you all can see my screen and hear my voice. Can you just give a brief thumbs up from your end to ensure that? Oh, thanks. Thanks. So, before starting today's problem solving session, which is for the third week content, I would like to answer two questions that I was unable to answer in the previous session. The first one is the why when we have a large block length we are able to decode our signal even with lower SNR. It actually fundamentally arises from the Shannon capacity, which says that um if your transmit rate is below channel capacity, you can transmit it with arbitrarily low probability of error, but there is a crucial catch here, that is when the block length is infinite. So basically when I mention large block length for 5G, it corresponds to like 4000 to 6000. So that approaches that infinite block length. So basically that allows you to reach capacity. So the issue is when you have you can intuitively see it like that, when you have a large block length, the you can actually have the benefit of coherent integration. That means the you can average over noise over a large code length, or you can see it in that way that when you have a short block length, the probability of a noise flipping one of your bits is relatively high. But at the same place, when you go for a larger block length, you will see that that effect of noise flipping one of your bits is kind of getting diluted. So for the same code rate, your block error rate will be drastically lower. So this is what allowing you to decode the signal under low SNR. That's the benefit we usually have when we have a large block length. But large block length have like we cannot infinitely really increase the size of block length. We have seen the reason for that. We need to do transport block segmentation and all that where it's required. And the second question is about which of the block in the transceiver chain is the responsible for removal of filler bits, which basically carries no information at all. So that I would like to answer in today's session. So let us start with that. So week 3 we have seen the use of rate matching block. So can one of you point out what is the necessity of having a rate matching block? Why do you exactly need that? Like what I am asking that why we need the rate matching block in the first place? Anyone?
To adjust the code rate to the user specific code rate.
Yes, and this is because LDPC encoder or decoder can uh, generate or like encode or decode at a particular code rate, right? And what this particular code rate is called?
Mother code rate 1 by
Mother
3.
code rate. Okay. So there is no guarantee, actually there is very low probability that user is going to ask for exactly that code rate. So that's why we basically need red matching block true. So let us consider a hypothetical situation, like let's say suppose I take a number, some hypothetical number that goes into the input of LDPC encoder here. Let us consider this is a LDPC encoder. Let's say what goes here is a block length of size, let's say 6000. So what is the output is going to be for, let's say, base graph 1. If I consider I'm operating on base graph 1, output code length size. Okay, let me make things a bit more simpler. I have at input I have 22 systematic columns and times some lifting size ZC. So what is the output going to be for base graph 1?
66 ZC.
66 ZC. So that is other code rate is satisfied here, because here it's 66, it's 22, so 1/3. Okay, fine. So essentially I am getting somewhere close to 18,000 bits here in a block. And let's say the user requirement is lesser. Maybe user is looking for only 12,000. So how do you exactly plan to achieve that? How do you do it? Okay, before getting into that, I have one more question here. Whatever goes here in the LDPC encoder, that should have a fixed size, right? So often the information bits cannot satisfy the constraint, so we need filler bits. But filler bits are basically null bits, right? So how do you exactly feed that thing into LDPC encoder? Because it can, LDPC encoder can operate on binary numbers, that is 0 and 1s. So how do you handle the situation? Filler bits are null bits, and null bits cannot, definitely not go into LDPC encoder, because encoder can only operate on zeros and ones. So how do we solve it? So we basically replace the filler bits with zeros and feed it to LDPC encoder, and the encoder output we again add them, because their position remain kind of fixed. So here my issue is LDPC encoder is generating 18,000, but I need only 12,000. So of course we have the common sense approach is to we'll send less, but what less? That's the question. So here the concept of circular buffers comes in. So circular buffer is nothing, it's basically means you are going to write this all 18,000 bits in a circular buffer kind of thing. And but you need some 12,000 odd numbers, so of course you are not going to send all of them. So which one you are going to send? So here comes the concept of redundancy versions or RVs. So suppose your entire content is written in the circular buffer, so it's just a memory kind of thing. So, and when I say redundancy versions, so those are defined as like RV0, RV1, RV2, like that, and each one of them has some starting point and some offset where they starts from. For example, if I consider this starting point as 0, so you can consider this is as RV0, and I consider this one starting point for RV1, this one here RV2, and this one here maybe RV3. So even if I mention here the starting point as 0, that need not be the case, because often you have seen that to achieve high data rate, or to improve the efficiency of LDPC decoder, we can see that often we have to start from certain offset. Like basically we can puncture some bits. When I say puncture, I mean just I will ignore certain bits. So my offset could be like let's say uh, 3ZC. So instead of starting from 0, I'll start from 3ZC. So that means I'll basically ignore the first 3ZC minus 1 bits. So that way my performance can sometimes really improve. But the issue is here scheduler, which is basically sitting in the Mac layer, which covers the intelligence part, that decides that if I have to send 12,000 bit out of 18,000. Of course the question comes, which one should I send first or second? So can one of you point out, like what do you think, like for initial transmission, which version should we send? Or okay, let's forget about the version, like which bits makes more sense to transmit at the first transmission?
Systematic bits.
Yes, so that is systematic bits is nothing but the uh, parity bits or the message bits. Which one?
Message bits.
Message bits. So information is more crucial. So basically we are going to transmit as many message bits as possible at the initial transmission, and see whether the transmission is sufficient. So what happens if, let's say, your uh, let's say you transmit as many message bits as possible at the first transmission and some parity bits, but let's say at the receiver end it's not sufficient enough to decode. So what the receiver is going to do at that case?
It will ask for retransmission.
So it basically transmit a NAC or negative acknowledgement and ask for retransmission. And then what are we going to retransmit? Like some another version or the same version again?
Another version.
Can be same or
Another version. Okay. So are we always going to send the same another version or the same version, or what is the criteria for deciding that?
The next one in the circular buffer.
Okay, so that's essentially saying that sending the another version, that is RV1, that's okay. I'm just saying that are we always going to send the next version, or there is something else that decide? Let's say I am employing certain version of hybrid ARQ. Let's say I would like to implement the chess combining thing. So in that case, what I will do, I will send the next version, or I will send something else.
you send the same.
Okay, so it depends on what version of hybrid ARQ I am implementing. If it's chase combining, if you remember the principles, we basically transmit the same thing again and again. And if it's incremental redundancy, then of course we resort to the next version, like RV1, RV2, or RV3, and we'll see. So that is one scenario when your whatever user ask is less than what LDPC encoder produces at the output. What is the opposite scenario? For example, I have let's say the user rate is asking is low. So basically I need to send now 24,000 bits, but I am producing only 18,000. What I will do in this situation? Your basically low code rate means you have to transmit more and more parity bits. So essentially it's now it's 24,000 bits it needs for the same number of message bits, but LDPC encoder only produced some 18,000. So how do we manage now? We know how to transmit less when we have more, but when the situation is opposite, what do you exactly do?
We can repeat.
We will repeat. Okay, that's the circular buffer. Use of circular buffer makes sense here because we'll start from here. Once we reach here, it's 18k, and then we'll keep repeating it until this condition is satisfied. Like basically until we transmit 24,000 bits, right? Okay, so this is the concept of rate matching. So now is a good time to ask that is it possible to remove the filler bits at this stage, or filler bits are required, so we cannot remove really them at this stage. Okay, let me ask you in this way, like why do we need filler bits in the first place? What is their purpose?
To match the input length of LDPC.
Okay, so you are saying that LDPC encoder can only take in certain fixed length, so that's why we need filler bits in the first place. So basically after we have the LDPC encoder output, so is there any need for them or not?
There's no need. You can
It's not
puncture.
needed. Okay, so basically we can remove them, right?
Yeah,
So at which stage we remove? Rate matching block or some upcoming blocks?
rate matching.
Rate matching. And how do you remove them exactly? When I see things in the context of circular buffer, so we are saying that we are writing the output of LDVC encoder in a circular buffer. So how is the procedure of removing filler bits happen here? So actually we are aware of the position of filler bits, where they exactly are. So, and we are writing the LDPC encoder output sequentially in the circular buffer one by one. So when we come to that particular position index of filler bits, we basically skip them. We don't write those information in the circular buffer. That's how the removal of filler bits happen. So what is the next block that comes after rate matching in the transmitter chain?
The interleaver.
Interleaver, correct. And what is the purpose of using interleaver? Why do you need it?
To spread the burst error.
To spread the burst error. And if you don't spread, what is the issue?
LDPC decoding becomes difficult.
So LDPC decode, you are saying LDPC decoding is poor at handling burst errors.
Yeah,
So that's why we'll need interleaver. So in some way, some mysterious way, it will spread the bus error thing throughout the block length. So what is that way out here? For example, if you need to answer this question here, we have a certain bit sequence of length 16 and our modulation order is, let's say, 16 QAM. So how we should interleave this bit sequence, or basically what is the output of interleaver block here for us? How do I proceed? I am given the bit sequence, I am giving the modulation order. What should be my output? How do I get it?
We have to divide it into 8 bits plus 8 bits. Write the second 8 below one, and then we have to read vertically and write horizontally.
Okay, so you are saying something like this. I have this 16 bit here. I'll group first 8. So sorry, I don't have 16. I have only 12. So I'll group first 6, right? That ends here.
Yes, first 6. Yes.
So 1 0 0 1 0 1 0 1 1 1 1 0. But what is the role of modulation then? Modulation, which modulation scheme I am using basically? Does that information plays any role here?
Yes, I think we have to add more zeros to make it 16.
Not exactly. So actually you can see here, as you have mentioned, there are two rows here, right? So your modulation scheme actually decide the number of rows. Modulation scheme decides the number of rows. So when I say 16 QAM, how many bits per symbol?
Yeah, 4.
4. So 16 QAM means you are saying my modulation order is 4. So that suggests I basically should have 4 rows here. So to have a 4 rows with a input sequence of 12 bits, how many bits per row I can have? We have input bit sequence of length
3
12.
bits.
3 bits. So it's like I need to pick first 3 here, 1 0 0, then the second 3, 1 0 1, then the third one 0 1 1, then the last one 1 1 0. And now how do I get basically the interleaved output? I'll read vertically, right? Like this order. So essentially it will come out 1 1 0 1 0 0 1 1 0 1 1 0. So that is what my interleaved output is going to be for 16 QAM. But what if I change my modulation scheme to QPSK? What happens then? Now I am not using 16 QAM anymore. Let's say my SNR is low, so user requested for QPSK through some lower MCS index. What should my interleaved output be? How do I find it?
Have to group into 2.
Okay, basically you are saying there
Two
should be
rows.
2 rows. So how many bits per row?
6.
6. So then this will be applicable, right? And what is the output for this?
Yeah.
1 0 0 1 0 1 1 1 0 1 1 0. So that is be my interleaved output for QPSK, and this one for 16 QAM. Both are not same, right? So you have to
Now it is clear.
sorry, I cannot hear you. Can you just repeat once?
I'm saying the concept is clear now.
Okay, got it. got it, got it. So we have to pay attention to the modulation order that is also given in the I don't know, in the assignment questions it may be like QPSK or 16 QM or 64 QM, so we have to move accordingly. So interleave output depends both on my input sequence and very crucially on the modulation order also. So with that, so what is the next block used after interleaver?
Scrambling.
Scrambling. So you have interleaver, so that basically improves your performance in terms of handling the burst error. That's okay, but then you are saying another thing is there, that is scrambling. So what is the purpose of that scrambling? Like basically why do we need scrambling in the first place? We have already taken care of burst error thing, right, by interleaving. Why scrambling now?
To meet power constraint. To meet power constraint.
To meet power constant. What can you elaborate on that, please? Like what kind of power constant we are talking about here?
The unit energy requirement.
Unit energy requirement. Fine. So basically you are saying that average power should remain unity while
Yeah.
transmitting a large bit sequence. Fine.
Sequence.
Okay. So why it is necessary? Like can you just give me a practical example that okay, this is the thing it's violating, so this is why it's required like that.
Maybe the input bits are zeros.
Okay, so let's assume there are a lot of zeros at a sequence, let's say hundreds or thousands, because we have no control over whatever the input bit sequence coming, right? So okay, so we are having, let's say, a lot of zeros. So what is the issues there?
Only one constellation point will be used.
Okay, only one constellation point will be used. Let's say for to denote all zeros, basically a constellation point is used when it's very low power.
Yeah.
Fine. So okay, let's take the opposite example. It's easy to understand. You have a larger sequence of ones. I'm taking just the situation proposed by you, just the opposite, like large sequence of ones. So basically the highest constellation point is used. So what is the issue with that?
Higher energy always. You are transmitting at a very high energy.
You are transmitting at a very high energy. Okay. So if I am to, so basically you are doing scrambling. So is that scrambling really required if I am using, let's say, QPSK?
No.
Why is that?
All the points have the same energy.
So QPSK, what are my like possibilities of transmission? Like what are the four groups? Like 0 0,
0, 0.
0 1, 1 0, and 1 1. So this one corresponds to, let's see if I draw the constellation scheme in the complex plane. So these are the 4 points, right, I have. And when I say power of a particular constellation point, how do you get that?
You find the norm.
To find the distance from the 0, or in other words, to find the norm. Fine. So what is the good thing with QPSK? That it don't require scrambling at all of them has unit power, right? So even if I transmit a long sequence of particular bit here, my power is always going to be remain same, right? No matter I'm transmitting 0 0 or 0 1 or 1 0 or 1 1. And even if a long sequence of zeros or ones comes there, the average power always remains unity. And can you from this diagram only, can you point out what is the issue with higher constellation point, like why it's difficult to maintain the same thing as QPSK at higher constellation points, so such that my average power violates this unity constant and we need to go for this scrambling and all that. So QPSK we have these 4 points, fine, we are seeing that it has unit power, so no issues. No matter in the long sequence of whatever symbol you transmit, your average power is always going to be unity. But from this constellation diagram, how do you see that what is the issue with higher order modulation schemes such that they fails to maintain it by themselves, so that they need that scrambling thing?
The distance are different.
So distance are different. Okay, so let's say on top of this 4, if I add another 4 now, can be seen as 8 QAM kind of thing. So now you can see that this distance here and this distance here are not the same, right? So it's what you are pointing out. So if I transmit,
Yeah.
so if somehow in my transmission this symbol appears in a long sequence, that can very well happen. So I have to essentially transmit at higher energy, right? But transmission always happens at some average energy. Let's say your average energy is let's say 5 watt, and this transmitting this constellation point in long sequence will require you somewhat like 8 watt. You cannot satisfy that. So that's what. So how does scrambling helps to mitigate this effect? Let's say you have a long sequence of ones, 1 1 1 1, lot of them. This is my input sequence with some modulation scheme other than QPSK. Other than QPSK. So how scrambling achieve, like, handles this? What does it do? Let's say my interleaver output is this, that somewhere in between a long sequence of ones appears, and the modulation square is the modulation order is, let's say, 16 QM or 64 QM. So the thing is mentioning that higher energy constellation point is transmitted for a long enough time. So how scrambling helps me out here?
Lower points and higher points will be used equally.
True. So in a large spell, if we see over a time span long enough, that is enough for averaging. So that will be converted to higher and lower constellation, so that average power always remains constant or unity if you normalize it. That's true. I'm saying like let's say we are talking about zeros and ones, right? So how do we achieve those scrambling, like how to implement it? What you said about the from the intuition point of view, that's completely right, that's fine, but how do we implement this scrambling thing in practice? Like I'm having a large sequence of ones, what I need to do here?
You use pseudo-random counts.
Okay, I'm using a pseudo random sequence, fine. Pseudo random sequence. So why this random term here? Random means basically it's 0 and 1s can appear anywhere anytime, right? That's what you mean by that. It doesn't have a specific pattern. And what does pseudo represent here? Even if it's random, we kind of know exactly what this random sequence is. So randomness is in the nature of the sequence, but pseudo part comes where we actually know the pseudo random sequence. So fine, we have the pseudo random sequence, we have the input sequence also. Now what do we do?
XOR operation.
XOR operation. So if you have a large sequence of zeros and ones, you will XOR it with some pseudo random sequence, and in the output, so at output what is going to happen? So let's pick this particular example. Like there are a large sequence of 1, and since it's a pseudo random sequence is of same length as input sequence, and since it's random, I am considering that zeros and ones appear with 50% probability. So what happens then? Your input sequence are all ones, your pseudo random sequence are 50% zeros and 50% 1, but we don't as of now have no control over the zeros and ones where they appear. So what will happen to the output sequence? What the XOR operation do?
It will be different from the input in all cases.
Yes, true. So XOR operation basically
Yes.
when two input bits are same, it basically output 0, right? So when I talk about the input sequence, it's already fixed all ones, and pseudo random sequence I'm assuming that 50% times it's zeros and 50% time it's ones. So whenever ones appear in the pseudo random sequence, the XOR operation basically going to flip it into zeros. So the output sequence will be now consist of zeros and ones. So what I was willing to do to break the sequence of many ones, that chain is now broken. So it's not anymore the higher constellation point for a long span of time, but it is kind of distributed. Sometimes it's this, sometimes it's this, sometimes it's this one, but on average this unity power constant is maintained. So that's what we can achieve via scrambling, and scrambling is required for modulation scheme above QPSK. For QPSK scrambling holds not any value here. You can consider it as a like unity. It will let pass whatever comes through it, but for other modulation scheme it's required. Okay, so let us answer a few questions here. Here it's said that user is assigned 24 PRBs over the entire slot for physical downlink shared channel, and the modulation scheme is also given. Transport block size is also given 8986. We have to calculate the value of G. So what is the value of, like, what does G denotes here? Basically the number of bits that can be transmitted, right? So
Transmitted.
how we calculate it? How do we get that? So it's given 24 PRVs. So you have any hint from there to start from?
You multiply the number of PRBs by 12.
Okay, let us start from here. One PRV means how many subcarriers?
12.
12 subcarriers. And when they mention that one PRV over a slot, that means how many subcarriers now?
14
So 12,
times 12.
12 subcarriers, and it's given over entire slot, so that multiply with 14 symbols,
12 to 14.
that gives you some 168 subcarriers. But are all of them used, can be used for transfer of data, or some are reserved for some other purpose like control information or pilot transmission, whatever?
Some are reserved for DMRS.
Okay, so the number is 6, right? 6
Yes.
subcarriers are reserved. So for data transmission, we essentially have 168 minus 6, 162 subcarriers. We are doing 16 QAM, so that means how many bits per symbol here we have?
4 bits.
4 bits per symbol. So 1 over 1 subcarrier, we can transmit one symbol. One symbol carries 4 bits, and we are given 24 such PRBs. So what is my G here? That is the number of bits can be transmitted. How do I calculate that? You are mentioning that number of PRBs. Okay, number of PRBs times what is the next parameter here? The number of subcarriers in PRB, right? That we mention number of resource elements also. Number of resource elements. And what is the number here? We have already calculated
162.
162. And and this is the number of symbols you can transmit, number of symbols, but we are asking about number of bits. So what should I multiply this with?
By the 4 bits.
So number of bits per symbol, that is 4 here. So we have 24 into 162 into 4. Let us calculate the number. 24 times 162 into 4, that comes out to be 15552. 15552 bits. Okay, with that let us move to the next question. The first part remains same, that now we are asked to find the size of rate matched code block. So how do I get that answer?
So here we are not considering PDCCH in first symbol. We are completely taking as PDSH all 14 symbols. Huh?
Yes, yes. If we consider like entire thing is dedicated to data transmission, that translate to 168 subcarriers for one PRB, but 6 are removed for pilot anyway. So we have for effective data transmission only 162 subcarriers per
Hello,
PRB.
am I audible? Hello,
But technically it is not
hello.
possible, right?
Yes, some certain things are need to be reserved for control information, of course.
Okay, okay.
Hello, am I audible?
Yes,
Hello.
yes, yes.
Yeah,
Yes,
yeah.
you are
So,
audible.
so there is one question. There is one thing that is asked in assignment.
Yes,
That assignment says that uh, assume that in each PRB, 6 REs are allocated for DMRS.
yes.
So for each PRB, it's saying. So what? How do you decode it?
Okay, whenever they don't mention over the slot, so we assume when it's mentioned one PRB, that means one PRB over the entire slot. So for if we consider one PRB mean 12 subcarriers, and if nothing is mentioned, we consider one PRB over entire slot. So that is 14 symbols times 12 subcarriers, 168 resource elements. So among these, four, sorry, 6 are reserved as you mentioned for DMRS. So only 162 are available. 162 resource elements are available.
No, no. So the question is, I mean, something different. The thing is, whatever information that was given in the your question is the same information.
Okay.
Additional note is given. Note,
Hmm.
assume that in each PRB, 6 REs are allocated for DMRS,
Yes.
like that.
Okay. Okay. So here we already assume that thing, but the calculation I guess will remain same only. Like in
So no, it is for each PRB we need to subtract 6, or overall, I mean, in over a slot, I should subtract 6
okay,
to
overall the
complete.
slot. Oh yes, overall the slot.
So, but it's given. I mean, the in the note it gives for each PRBs 6. I mean, 6 REs are allocated for DMRS.
Okay, okay. So that I got, but the when they say one PRB, so we need to assume that one PRB is they are talking about 12 subcarriers over the entire slot, uh, 14 symbols.
Okay.
That's what my understanding is. So it's not here
Okay.
only 12 subcarriers. It's 12
So
into
should we
14.
subtract 6 from 12 and then take 6 REs per PRB, or
You have
we should
to
multiply, find out entire RE and then subtract 6?
entire RE and then subtract 6.
Okay. Okay. Okay.
Okay. So here how we are supposed to find the size of rate matched code block here. We have already calculated the number of the bits to be transmitted. So that is 15,552 somewhat. Our transport block size is given here 8986. We have to calculate the size of rate matched code block. How can I find it?
First, we have to find the number of code blocks.
Number of code blocks, fine. So if I denote the number of code blocks as C, how do I get it?
It will be TBS plus CRC divided by maximum code blocks minus CRC.
So it's like 8986 plus 24 bit CRC, the whole thing divided by
8448.
8448, that is the maximum input code
Yes.
length size to LDPC encoder, minus 24.
Minus 24.
And I have to do something else here like a ceiling operation or flooring, because this term is coming out to be a fraction, right?
Yes.
So
We have to do. We will do a sealing after that.
yes. So essentially the results will come out to be two. There are going to be two code blocks here.
Sir, do we
Yes.
need to add that 24? Do we need to add
Uh, do I need what? Can you mention once?
to add the 24 bits? Do we need to add?
Yes, because you have transport block, there is going to be a transport block CRC, right? So essentially if we have a transport block of size 8986, so we need to append 24-bit CRC, so that will become my effective size, and 8448 is the, so this is my supposed input, and 8448 is the maximum LDBC encoder can handle, among which 24 must be CRC, so you need to subtract. So this is my effective data, even if there is a CRC included here, and this term here also takes into account for the CRB, so you need to be subtracted. So that's account for the effective data that you can have in the TV, and then you have to divide the whole thing. So let's say if I have a transport block size of 8 4 4 uh, 8, what do you how many code blocks you think we need for it? My transport block is 8448, right? So and LDBC encoder input size is also 8448, so what needs to be done here? What can you do?
It will be 8448 plus 24 divided by 8448 minus 24.
Yeah, so it's effect, even if I have 8448 data, I cannot directly feed it to LDBC encoder, because the transport block CRC have to be appended, and the moment I add 24-bit CRC, it crosses the maximum size. So you have to account for that. The segmentation is required, even if your pure information bits are 8448. Is the question you ask is answered, or
It's okay.
okay, thanks. So there are two code blocks we have, and how do we find? Yes.
You can complete first, then I will ask.
Okay. Okay. So what should be the size of rate matched code block for us here?
It will be G by C.
It
That
will
means
be
1552 divided by 2.
G by C here. So that accounts for 157 again, 7 again here, and 6. So I have one question here. So why do we need not like take into account for filler bits thing here? Like we are we usually do that, but why it's not required here when calculating the size of rate matched code block?
The filler bits will be punctured. So
Yes, so filler bit is always in the context of LDPC encoder or decoder. So once you reach the rate matching block and consider its output, so filler b is kind of added and also removed, so its effect of basically null. It doesn't hold any significance here, so that is why it's not required. True. And someone is asking a question.
Yeah, I put a related question on the chat window.
Okay, okay, I'll just see it. For 12, 13 and 14 WebDM symbols, how many CRC bits we need to take in calculations?
Actually, in some books, they are always taking 24. In some books, for 12 and 13, they are taking a 16 bits for CRC. and when it is 14, they are taking as 24. So, but there is no standard defined. The 3GPP doesn't define it like this. It has
Okay.
become a general practice, but I'm not sure how to use it in calculations. Whether we have to take always 24, or for 12 and 13 we have to take 16. That's a confusion.
Okay, okay. So, if I remember correctly, this course when the CRC thing is first introduced, it's mentioned that it's either 16 or 24-bit CRC,
16,
but
yes.
then onwards we are always seeing for be it for transport block and be it for code block, we are always going for 24-bit CRC.
Okay.
So, my feeling is that unless and until it's explicitly mentioned about 16-bit CRC, we can safely take 24-bit CRC and move forward.
Okay, got it. Thanks for the clarity. So that means for our calculations, we will be always taking 24.
Yes, yes.
Yeah, okay, thanks.
So let us move to our next question here.
And while calculating C, I have also cross-checked also if I take TBS plus CRC as 16 divided by minus 16, the answer is the same as 24. So it doesn't make any difference at this stage.
Okay, okay.
Also, it's exactly same. It's
Yes, yes,
never
yes, yes,
any
yes.
difference.
That's true. Because like these number of CRC bit are too small, like compared to the maximum size or the input transport block size to have any yeah, like significant impact on them, no matter if you put 16 or 24 here. The numbers on the left hand side and the here maximum number are always going to be uh, big enough usually. So this question here asks about the correct ordering, but one thing I'd like to point it out, it doesn't talk about the transmitter chain, it talks about the receiver chain. Even if the receiver chain is not introduced in the lectures until week 3, I guess week 4 onwards it might be introduced, but we can still extrapolate the ideas from the transmitter chain and see pick the correct order. So what about the first option? What do you think? Is it the correct one? If we talk about from receiver end, the correct order of processing. I mean, what is going to be my first task? De-interleaving or LDPC decoding or demodulation? Which one?
Demodulation.
Demodulation. Okay. Then onwards it's become bit easier because the option is already given. But still I'd like to go for the order like demodulation. What should be the next task after demodulation?
Descrambling or unscrambling.
True. And then
Then maybe unconcatenation.
okay. So segmentation you were saying. I mean not the segmentation in the first stage of
Deconcatenation or whatever.
deconcatenation.
Yeah,
Okay.
inverse of
Okay.
concatenation.
Okay. And then
Then deinterleaving.
fine.
The,
Then rate recovery. Then LDPC decoding.
So which one of the option we should go for here? 1, 2, 3 or 4? Which looks correct?
3.
3. And so it's like you are saying de-interleaving, rate recovery, and then comes LDPC decoding and then concatenation. So can we and just try. Okay, let us first write them down. D interleaving, rate recovery, LDPC decoding, and concatenation. Can you try to fill out the intermediate ones, like if something comes before de-interleaving, as it's already mentioned, demodulation? Fine. So what after de-interleaving here? Okay, after demodulation, is it straight de-interleaving or something else? So after demodulation, we need to go through. We need to go to descrambling, right? Then comes de-interleaving. What after de-interleaving?
Segmentation, code block segmentation.
Okay, we mention it as deconcatenation, and then comes rate recovery, or something in between is there? So after deconcatenation, it's rate recovery, fine. After rate recovery, it's LDPC decoding.
LDPC decoding.
So is filler bit insertion required here or not, like in transmitter chain?
Yes, required.
Okay, it is required, fine. What after LDPC decoding? Is it concatenation straightforward, or there are some intermediate blocks also?
CRC validation.
After LDPC decoding,
CRC validation and then concatenation.
then comes concatenation. Okay. So let us move to this question here. It's given 150 PRVs. Okay, there should be a if here. 150 PRVs are allocated over 14 symbols to transmit a PDSCH with transport block size given as 32984 using 64 QAM. We have to calculate the circular buffer length for each code block if the LDPC encoder is using base graph 1. What should be my circular buffer length size? So when they say circular buffer length, what does they exactly refer to?
RV.
Circular buffer length.
The output of LDPC.
The output of LDPC decoder.
LDPC decoder.
Okay, fine. And for base graph 1, is output of LDPC decoder fixed, or it has some expression?
It is 66 times
66 times
lifting size.
lifting.
66 ZC.
Okay, 66 ZC it is. So my only unknown here is ZC, and how I am supposed to find the ZC here? Where should I start from?
First we have to calculate C,
C. Okay.
the way we did earlier. TBS plus CRC divided by maximum TBS minus CRC.
Okay. There is a number of code blocks calculation.
I think below it will be
Yes,
8448.
yes. Sorry about that. 8448. So it appears to me it will be 4 only. Fine. So what next?
Find K. You find the new
Okay, and how do I do that?
transport. There will be B initial plus 4 times 24.
Okay, so you are saying 3 2 9 8 4 plus 24, that is transport block appended CRC size, plus
Times 4.
4 times 24. What is this 24 is? Is that also transport block CRC? This 24 here? Okay, let me ask in a different way. What is the difference between this 24 here and this 24 here?
One is CRC, the other one is TB.
Which one is TBCRC?
TBCRC, the first one.
First one is
The other one is
TBCRC.
CBCRC.
So you are
Yeah.
saying first one is TBCRC, what you attach to the whole transport block, and second is the CBCRC or code block CRC that you attach to every code. And K is the number of bits you have without filler bits, right? Without filler bit. So that is your effective
Payload length.
yes. So that would be like 5 into 24, that is 120 added with 32984, 33 1 1 2 or 108, sorry. Not even 108, I guess it's 16 here, so 104,
104.
33 104. Okay, now what should be my procedure? I have 4 code blocks. I have total length of 33104.
I think in the notation this will be B dash, effective
Okay,
payload length.
okay, so let's make it B dash here. Thanks for the heads up. Then what is my next step?
Then we have to calculate K B dash divided by C.
Okay, K is equal to
Then
B
it will be
dash,
without filler bits.
B dash divided by C. Thanks for this. that is 8 here, 1 1 2 3 0 7 2 4 6. So total 8276 bits. Let me introduce a slide here. 8276. So what is the input to the LDPC encoder size? LDPC encoder input size is 22 ZC, right? And the max size for our reference for base graph 1 is 8448. So how I am supposed to find the ZC here? So effectively my 22 ZC should be more than 8276, right? Or ZC need to be greater than 8276 divided by 22. 377. So from this table I am supposed to find a number greater than 377, and there are not many options, only one, that is 384. So my ZC choice is 384. So if ZC is 384, what is my circular buffer length going to be?
Uh, 66 ZC.
66 times 384. That is nothing but this 232, I guess. I just need to calculate it once. Okay, 25344. 25344. So circular buffer length for each code block for base graph 1 is 25344. Now I have one question here. If the assignment question modifies it to, let's say, base graph 2, so is it true that only change I need to made here in terms of 66, it need to be some other numbers, and that's all, we can get it over with?
Most probably, yes.
Okay, let us start it.
The code block needs the code block number of code block needs to change also.
Okay, so base graph 2 we are talking about. So what are its parameters? Its parameter is maximum input size. What is the maximum input size for base graph 2?
That H40.
3840. And what is the output length? 66 ZC or something else?
56 ZC.
It's actually 50 ZC actually. So we need to start from here. Now this number will change. So from instead of 8448 it needs to be 3840. So let us see. C is going to be 32984 plus 24 divided by 3840 minus 24. And that turns out to be 984 9 code blocks. Let me separate this out, this calculation here. So my payload size is going to be 32984 plus 24 plus 9 into 24. So 3 it's going to be 240 216, and the K here is going to be 33216 divided by 9.
Just check, it is 33224 or 216.
Okay, sorry, yeah, it's 224. 16 minus, so 224. Thanks for pointing out this error here. 224. So it will come out to be 362 62. Okay, did I make any error here?
So 3691.5. So that is 3692.
Okay, just yes. So you're getting 3692, right? Okay.
Yeah, 3692.
And it's 3840. So my what is the input size for base graph 2 here? In base graph 1 it's 22 ZC. Here it was, can one of you point out? It's actually 10 ZC. So this 10 ZC is supposed to be greater than 3692 here.
What is this 10 ZC?
Sorry, I didn't get Okay,
What is this 10 ZC?
okay, 10Z is the input to the LDPC encoder size for base graph 2. For
This
base,
is standard.
yes,
We
yes.
are just taking.
Uh,
Okay.
no, no, it's standard. Like for base graph 1, your input is arranged into 22 systematic columns, but the number of elements in the columns is not fixed, so it's 22 times ZC, right? For base graph 1,
Okay.
and in
Got it.
output you will get 66 ZC, so that is a mother code rate of one third. When it comes
Okay.
to base graph 2, your input size is 10 ZC and your output is 50 ZC, so that is a mother code rate of one fifth. So that's what.
Actually, in the table, it is written 13 ZC.
uh, 13 ZC, okay.
For RB1 is 13, 25, and 43 for BG2.
uh,
13, 25, and 43. The table we got in the assignment.
the table you, okay, I can you just copy paste it once and in the chat box, because I haven't seen that.
Okay.
Yeah, sure, thanks.
It, it's an image, and chat box, I
Okay,
think
okay,
it's
okay.
not allowing me to put
They're
the
not
image.
allowing. So
Yeah.
can you just share your screen once? Like,
Okay. It is visible.
yes, yes, it's visible.
This one.
Okay, okay. These are
Oh,
the
it is
your
13, 25, and 43.
that I got it. That are actually not your in not related to encoder size there.
Okay, okay.
These are
It is for RV.
yes,
Yes.
those are starting indexes of the redundancy versions.
Got it. Got it. So they are different.
Yes, yes, yes. So your
Okay.
LDBC output decoder size you have seen, of course, that is output is 50 ZC, and since for base graph the mother code rate is one fifth, your input size is 10 ZC. So input is going
Okay.
to be arranged into 10 systematic columns, but and ZC is of course lifting size.
Sir,
Yes.
in that formula, what is the NCB?
Which one? Uh,
The one that was shared a moment ago. Calculating for the redundancy version.
Okay, you are talking about the starting index of redundancy version that we just
Yeah.
seen. Yes. So, can you just repeat your question once? I didn't understand it.
What is that NCB? The meaning of it?
Okay. Actually, I need to see it again exactly to. Uh, can
It
like
is
if
size of the LBC encoder. NCB is N. NCB is N in the class that he has specified.
okay, okay,
NCB is N. So it is 66 times ZC.
But
Or
it
in
seems
this
like
case,
the two are cancelling. So
N is equal to NCB. Whatever variables those are used in the class, those are N, and n is equal to NCB.
So is the numerator and the denominator cancelling out?
Yeah, so it will cancel. Yeah, yes.
Then what is the essence of the formula?
Yeah. So in the remaining one, no, it might not cancel, right?
So actually, Dennis, I guess there are certain numbers for which it will cancel out, but there are also numbers
Yeah,
where they exactly
numbers
don't
which may not
cancel.
cancel. Yeah.
So you will
Yes.
do that ceiling operation there,
Mhm.
and it's pretty much the standard way of writing those things, so that they all are in
Okay.
same format.
I have a question on the previous slide.
Previous slide. Okay, here.
The
Yes,
previous one, previous to this, where the question was there.
yes,
So while calculating B dash, we always have to take it CRCS 24, irrespective of whether we are given 14 OFDM symbols for 13 or 12 in the question.
yes.
Okay. And in the terminology, I'm confused. What is the difference between K dash and K? For
Okay,
mother rate, they are using K, and for actual rate, it is K dash. But when it comes to these type of calculation, I'm always confused on K and K dash. But what do they exactly mean?
okay. So can you just give me a brief that like what they mention as K and what they mention as K dash? Maybe I'll, because I don't exactly remember that discrimination. Like K dash, is that K dash LDPC and LDPC encoder input size refers to, or with and without filler bits?
K dash is B dash by C.
Okay, K
And
dash
we have
is
to
B
find
dash.
out K, which is
K dash is B dash by C, but
uh, and we have
like
to find out K, which is greater than K dash, as per
okay,
the for the input to LBC encoder.
like for mother code rate, they are using K by N. It is not
Yeah.
K dash.
Yeah.
So
Yes.
now,
Correct.
what is the difference
So
between K and K dash?
K is 22 ZC or 10 ZC in this case for base graph 2.
That means, no, no, I mean to say, what is the meaning of K and what is the meaning of K dash?
K dash is, I mean, a size, any size, but K
Okay.
are fixed size depending upon
So
size
K is
which
fixed
is
size.
taken by
Got
LBC
it. Got it.
encoder. There are fixed sizes of LBC encoder. Yeah, so that is K.
Okay. Like K is 22 ZC, so that is
Correct.
fixed.
K is 22
Okay.
ZC.
Got it. Got it.
Yeah.
And K dash is variable.
K dash is, I mean, B dash by C.
Okay. Got it.
Okay, I
Thanks.
guess I make this notation confusing. It should be K dash here then.
Yeah, K dash. Yeah,
Uh,
K dash.
okay, thanks for this heads up.
So the 3692 is K dash here.
Uh, just a minute. Uh, okay. So here also you can see my ZC is coming out to be 384 here only. The maximum lifting size. But it can very well be something else. It all, but so we just need to be careful here. Just because they mention it base graph 2, that circular buffer length doesn't only becomes from 66 ZC 50 ZC, but the calculation should be again starting from here only. What is your transport block size? Because now the maximum code block length changes, so everything will change from here, starting from number of code blocks to the payload size to the number of effective bits you have in per code, and then the lifting size also. For this case it turns out that that is same for both the cases, but it can very well be not in some other example. So this question is the data is similar to previous one, so we have to calculate the redundancy version index for third transmission, that is basically RB2, if the LDPC encoder is using base graph 1. So let us write down all of them: rv0, rv1, rv2 and rv3. So we have already seen, using base graph 1, our LDBC encoder input size is 8448. So what is the starting index let me mention here starting index. What is the starting index for rv0? As mentioned in the lecture, it's 0, right?
Yes.
Yeah, it is 0.
0. And then for rv1, it's the ceiling operation is there, and what comes inside it, there is the number 17. What's
17.
and below it 66. So what else I need to fill up here?
17 NCB, 66 ZC.
66 ZC should be here, that the entire thing is okay. And here it's 67 NC. I'm mentioning at
NC.
again here.
And outside the bracket, it's written ZC.
And what should be there outside of this ceiling operation?
ZC.
NCB. Okay, ZC.
ZC.
For RV2, it's 33, right?
33. Yes.
What is for RV3? It starts from
56.
56. So we are looking for third retransmission, so that is not RV2, that is RV3, right? If we talk about third retransmission, okay, or RV2,
It will
because
be RV3.
yeah, because they are saying third retransmission, so that should be RV3. First retransmission is this, so I should have 56 divided by 66 times 384. 384 here, and here I should have 56 times
I believe it's not a formula. Actually, this defines the ZC, the actual value for RV divided by the maximum value. So maximum is always 66. For RV1, we have to take 17 ZC. RV2, we have to take 33 ZC. And for RV3, we are taking 56 ZC. This is how I have seen the calculation in most of our internal manuals.
Okay, okay. So you're saying this
But I think it is written like this only, but the calculation I've done like 56 ZC, 33 ZC, and 17 ZC.
okay,
So it will be 56 into 384.
56 into 384,
384.
that is
Let me calculate.
21504.
84. 21504.
21504. So what is going to be my effective code rate in this case? The effective code rate of LDBC encoder.
Effective code rate. think we have to start with the calculation of G.
Okay, calculation of G. So there are number of PRBs, that is
150
150.
PRBs into 64 QAM, so it will be 6.
Okay, 6 is there, and in between number of RDs, how many are there? Resource elements 162,
Resource elements will be 162 only, yes, 14 volumes,
and that
168 minus 6.
translate to 150 times 162 into 6, that is 1,04,5,800. This is the number we can transmit. And how many code blocks we have using 4 code blocks, right? We have already seen using base graph
Yes,
1. So 145,800 divided by 4.
divide by 4.
So that comes out to be 145,800, that is 36,450, 36,450 bits per code block.
Now the effective code rate will be K dash by E. K dash we calculated previously, so divide by this number.
So this is what we have, E, right? This number here. G by C is E, and you are saying effective code rate is K dash by E, right? Why it's not K, that is the LDBC encoder input size?
Filler bit.
Yeah, correct.
So they
Contains filler
don't
bits.
carry nothing, no information, it's just redundancy to fill out the
Parity.
place, right? So what is the value of K dash we have obtained for base graph 1? 8276, right? 8276 divided by 36,450. So 8276 divided by 36,450, that comes out to be 0.227, 0.227. So that is my effective code rate for this given resources and transport block size. So let us consider this. My transport block size is given as 40896, MCS index is given. Index is given means basically my effective rate is given. So I am supposed to calculate the PRBs required, part symbol. How do I proceed in this case? MCS 14. So what is my gain from that? You can have effective code rate. What is effective code rate for MCS 14?
It will be 553 divided by 1024.
553 divided by 1024. Okay. And next, what should I do? Do I need to calculate the number of code blocks here also?
Yes, we have to calculate C.
Okay. So let us calculate C. 40896 plus 24 divided by 8448 minus 24. So that will become 5 or 4. uh, 6 plus
It is coming to 4.85, so it will be 5.
okay, fine, 5 it is. We have 5 code blocks. And in each code block, what is the effective number, like payload per code block is going to be? That is k dash
Then, yes.
40896
Not
division.
K. I think it will be B dash.
Okay, so let's like make the division here only, so
Okay.
that would make it
Zero.
dbcrc plus
Plus
5
5
crcs,
into 5 into 24.
and that would become, this is 4 8 900 40920 120 4 1 0 40. Is that correct? And here it will become 8208. Calculation, I hope, is correct so far. So what should I do next from here?
So we know effective code rate.
We know effective code rate, true, that is
So which is equal to 0.540.
So I have this effective payload kind of thing per code block here. I know my effective code rate. So what should I do next?
So we need to find out code block size.
Code block size. Okay, how do you do it?
So 0.540 is equal to 8208 by whatever the required answer. So
You are saying 8208,
divided by 0.540 is the answer.
and this 0.540 you get by dividing 553 by
Yeah.
1024, right?
Yeah.
So that means essentially I am doing this thing, 1024 divided by 553.
Yes.
So what is the answer you are getting here? Can one of you please do the calculation and tell me?
It is 15200.
15200. 0 0. And my next step, what it should be?
Multiplied by C.
Multiplied by C. Fair enough. 15200 multiplied by C, that would give me 6800.
C is 5.
Sorry.
C is 5.
So what does the number gives me?
This
76000
is
bits.
G. This is G.
This is G. Okay. So G here is 76000. That is equal to number of PRBs. I am calling it like NPRB, resource element, since given PRB over one slot. And what is the modulation scheme used here?
MCS 16. Index 16 is what? 4.
Okay, so that is 4.
Yeah. 16.
Fine. Essentially it's 76,000 divided by 162 times 4. Of course I need to take the ceiling operation here because this comes out to be a fraction.
118.
118. Okay, so exact number is 117 point something, right? Or
Yeah, 117.2.
okay, so then it's 118 PRBs. So this many PRBs we need. So why do we exactly go here for K dash? I mean, why we are choosing 8208? Because the encoder input size should be 8448, right, for this one. So why you don't go for 8448 here? Why you only 8208?
Once again, same answer. Filler bits, right? Filler bits are of no use.
Okay, I asked already. Okay, sorry. Okay. It's a repetition. Sorry about that. Okay, so this one is a pseudocode given in the standard. So which one is correct for this? Like scrambling, interleaving, rate matching, or something else? We can ignore this part because this is
Rate
not
matching.
anyway
Okay.
covered.
Obviously, rate matching. This is a rate matching.
So, and how do we understand that? Like which part tells us about it that its rate matching is happening?
This computation of E and computation of E over here, which is G by C, ignoring all these multiplications and divisions in if-else.
Okay, so it's like basically we are going from one block to another. And what is ER denote here? I mean this term here, ER.
These are effective number of bits which will be transmitted per code block.
Effective number of bits transmitted per code block. Okay, can I say it also the rate matching block output for arithmetic
Yes.
code block?
Yes.
Okay,
Yes.
I guess that QM and NL is not covered in this lecture. It's mentioned
Yes.
what they are.
Yeah.
Data layers or modulation order, but okay, you can ignore those two things. So that's pretty much it for today's session. So if I answer any of your queries, I'll try, or we can conclude this session here. Or do you have any questions regarding the content of week 3?
What was the in the assignment given? What was the essence of being given the number of PRBs? Maybe that question was asked.
Okay, so you are saying like why we are supposed to calculate number of PRBs, right?
No, in the assignment.
Okay, in assignment, what is the question it's asked?
Just a minute. Just a minute.
Sure, sure, sure.
That final statement. Maybe in the chat box.
Okay, I'm looking at it. Okay, now
Yeah.
I see it.
Note. Assume that in each PLB 6 arrays are allocated for DMRS.
DMRS, yes, true. So when it mentioned, I think a bit clarification would have been required. So when they say each PRV, you could read it like each PRV over a slot. I mean, usually when we try to see what PRV is, it's 12 subcarriers, right? A group of 12 subcarriers. But PRV is also a frequency division assignment, so it has nothing to do with time division. So actually when we see each PRV, we are supposed to read as each PRV over the entire slot unless it's explicitly mentioned. If it's mentioned each PRV, we'll read as each PRV over the slot. So when we compute over the entire slot, there are 14 symbols, right? So if you try to visualize the OFDM time frequency grid, across the frequency division you have subcarriers, in the time you have symbols. So one slot, how many subcarriers are there? For a standard 100 megahertz bandwidth and 30 kilohertz of spacing, there are 3300 subcarriers, right? So in the y-axis there are 3300 subcarriers, in the x-axis there are 14 symbols. Now you group 12 subcarriers each, so it makes in y-axis you will have 275 PRBs and in x-axis you have 14 symbols. So whenever we see each PRB, it's like each PRB over the entire slot. So that makes each PRB is 12 subcarrier times 14 symbols. Each symbol you have 12 subcarriers. So that would make a total of 168 subcarriers. Now among this total 168 subcarriers, 6 are reserved for pilot transmission, and the rest, that is 168 minus 6, that is 162, those you can use for uh, uh, PSDCH, this thing, physical shared downlink channel. So when they basically what I'm trying to
So
yeah.
so that statement could have learned assume that 6 arrays are allocated for DMRS without.
uh, can you repeat yourself once? I didn't get it.
That statement, each
Yes,
PRB,
yes.
do we need it? Each PRB that
Yes, like it's like required in the sense we need to understand that we are talking in the context of a slot or subframe or frame, so that is required, right? I mean, each PRV means each PRV over a slot. That thing, if it's mentioned, it would have been much clear. So that
Okay.
statement is required, because unless it's not mentioned, you are prone to take all 168 subcarriers, right? So when they are saying that each PRV 6 REs are allocated for DMRS, you know that you don't have 168 subcarriers for the transmission. Sorry, it's not 168 subcarriers, 168 REs, the resource elements. You will have to reserve 6 for DMRS.
Okay. Yeah, I understand now.
So that is why I mentioned. Otherwise, if it's not mentioned, and if you don't exactly know that, okay, this is the like usually it's 6 subcarriers are reserved for DMRS, you will consider all 120 168 resource elements in one PRV. So that's not the case. We have to consider only 162 when it comes to uh, data transmission. 6 are reserved for pilot. So it's required in that way.
Okay, okay, okay. And one more question regarding exam. I'm
uh,
trying to register, but seems like the system can't accept my phone number.
okay, exam, you are saying the final exam registration.
Yeah.
Okay. um, I really don't know about the procedure. I mean, you have to contact the NPTEL guy, but I don't have like
Okay.
direct contact like something. So, like, what is the problem happening? Like, your phone number is not, they are not
The system,
accepting
the system, yeah, the system can only accept numbers from India.
India. Okay, okay. There is no provision for okay other countries number,
Yeah,
and that number is mandatory, right? Kind of.
yeah.
Okay. So maybe I would suggest you write a mail to them that okay, this is the issue I am facing, and I hope they will consider in a case to case basis, like send you some Google form kind of thing, or uh, I don't know exactly how do you handle it, but you can try writing a mail. Have you written the mail to this
Yes, I did.
okay, okay, and they replied, or
Yeah, I had to reply.
okay, okay, they are yet to reply. Okay. So, like, is it taking a long time? Like, how many days ago you did?
Yesterday.
Yesterday. Okay, I'd suggest you wait for another
And
2 3 days maybe, and then if it not sorted out, I'm just writing my email ID here. Just let me know, and I will try to forward a mail from my end also. I don't know whether they will reply or not,
okay,
but we'll see that. So I'm typing the mail ID in the chat box. Okay, just let me know
okay.
what is the progress in this.
And you also saying that we should also be doing MATLAB exercise. So
uh, I don't get.
when can
Can
we
you?
have when can we have MATLAB session?
Okay, okay, the MATLAB session. Okay, um, I'm yet to decide on that. Like, I have no information of such kind, but yeah, I told that I will try to hold one MATLAB session. Maybe after fifth or sixth week, we can arrange that one. I cannot really promise, but I will try to hold one a MATLAB session for this, and that I will let know in one of
Okay,
these sessions only. So I'll let you know much earlier, like usually a week before it happens. Okay. So
okay, okay.
okay,
Thank you.
sure, sure. Thanks. So thanks everyone for being with me for the session. And if you don't have any question, I'll conclude it. Okay. Bye. We'll meet on. Yeah.
Thank you.
Yeah. Sure. Thank you. So we'll meet again on next Saturday.